All right. So we stopped at this point in the previous lecture where we were trying to estimate the average precipitation over a certain area. So let's go back a couple of slides. So our interest is in finding out what the average or the mean precipitation is over a certain area. Inside that area, I have a few point measurements, right? And I want to use that point information to estimate what the average is for the whole area, right? So this area, as I said, could be any boundary of interest. It could be our campus, it could be the city of Tirupati, it could be the district of Tirupati, it could be the whole of Andhra Pradesh, it could be whole of South India, whole of India, whatever it is, right? So you can draw this bound. It could be a watershed. Okay, now that's a new word. We'll talk about that a little bit later, right? So one way of doing that is to just take an arithmetic mean of all the points that are inside my area, right? So if my area is, let us say, uh, Tirupati district, and I have 60 rainfall gauges distributed all over the district, then to find the arithmetic mean average for the district of Tirupati, I take those 60 points, do the arithmetic mean, and that gives me the average. That's one way of doing it. That's a fairly simple way of doing it. The smaller the area, the better it is, right? The smaller the area, the better it is to do an arithmetic mean. Okay, so somebody is late. They want me to admit them. Okay, I don't know why this is happening though. It shouldn't. Okay, so that's one way of doing it. The second way we discussed was the Thousand polygon method. Now, I tried to explain that procedure for doing the Thousand polygon. It's not very convenient to do it by hand, especially if the number of stations is large. But we did solve this particular example. Basically, you draw triangles and then draw perpendicular bisectors for all the sides of the triangles. And then you divide up the area into polygons. And those polygons, we refer to them as Thousand polygons. Okay. And then using the area of those polygons, we figure out what the representative mean is. So in this case, P bar, which is the mean precipitation over that area, is simply summation of Pi Ai divided by summation Ai. Okay, so that gives us the precipitation, mean precipitation over a certain area. Now, another way of thinking about this Thousand polygon method is to say that this is some kind of zeroth order interpolation. Okay, which means what am I doing? I'm just finding out the area. The procedure is basically this: you find an area in which all the points in that area have a common nearest rainfall gauge, right? And so that area represents the area that is covered by that rainfall gauge, right? Any point inside that polygon, the closest rainfall gauge will take that point will also take the same rainfall as the nearest rainfall gauge. So that's the idea behind the Thousand polygon method. And then we solved it and we got some answer, 121.84 centimeters. I've shared the slides with you. You can take a look at them again. Let me know if you have any questions. Any questions right now? Okay, what I notice is when I'm in the presentation mode, if somebody raises their hand using that uh, tool in your Google Meet, I'm not able to see that you've raised your hand. Okay, so last time something like this happened, I was teaching a class, somebody raised their hand, but I couldn't see that they had raised their hand. So what I request is that you unmute yourself. Then if you want, you can send it by chat, your question by chat, or just unmute yourself and then speak just right, because raising the hand is not working, especially when I'm in PPT presentation mode. Okay, other times it's okay. All right, let's move on. So now we're going to the method for finding the average precipitation over a certain area is the isohyatal method, right? So we already discussed what an isohyet is. An isohyet is basically a line that joins points of equal rainfall magnitude, right? So you draw a line which connects points which have the same amount of rainfall, and that line you're going to refer to it as an isohyet. Remember hyetograph? We spoke about that in previous week as well. So same idea is being extended. So let's show you an example of a isohyatal. People refer to it as the isohyet or the isohyatal. Both of them mean more or less the same thing. Okay. So Now these lines that you see over here, these are, where's the mouse? This line, for example, is representing the points along which the precipitation is, let's say, 10 centimeters. The next line is representing points along which the precipitation is 8 centimeters. And this one is 6, and this one is 4, and so on. And then here I have a 12, right? So we have these different points, which different lines, I'm sorry, which tell us what the precipitation is along that line, right? Now, once we have that, what we do is we figure out the area between the heights is. Like, so for example, let's look at this. So I have here, I have another boundary which is labeled as the catchment boundary, right? So let us say this solid boundary that you see over here is the area of interest, right? I want to know what is the mean precipitation inside that solid boundary. So what I do is I find the what is called the inter-isohyet area. So let's say this is the area. This is one area. And then this is the next area. And then this is the next area. And so on. Right? So using that area, what can I, any thought? Once I know that area, what can I do? Anyone? Tarun?
Yes, sir.
Yeah. Let us say I know this areas between two consecutive isohyet. Let us say I know this area. Okay. How will that help me find out the mean precipitation? Any idea? Any thoughts?
When the
Go ahead.
sir, no idea.
No idea? Come on. It's okay. It's okay if it's wrong. Don't worry. Anybody else? You all done integration of some sort, right? What is integration? Integration is basically finding the area uh, uh, area under a curve or whatever it is. In this case, I already have the area between two lines, those two curves. Now, this is some form of integration where those lines have a certain value, and then I'm trying to find out the representative average. Can I not take that area and say one end of that area represents a rainfall of 10 centimeters? So let's say take this first one, for example. This end of this area represents 10 centimeters. The other end represents 8 centimeters. So this area represents on average. Sorry, say that again. 9 centimeters. Exactly. So you take that area and take the average of the isohyets at the two ends of that area. That gives you that the representative average for that area. Then you do that for the next area, do that for the next area, and so on. Add them all up, you're done. Right? So that's exactly what we do. We use the inter-isohyet area. So let me show you the form. So P bar, which is the average precipitation, simply A1, which is the area between the first and the second consecutive isohyets. Multiply that by P1 plus P2 by 2 plus A2, the next area, multiplied by P2 plus P3 divided by 2, basically the average between those, and so on until the last isohyet, right? Plus A n minus 1, which is the n minus 1th inter-isohyet area, multiplied by Pn minus 1 plus Pn divided by 2, right? So if you have n isohyets, you will have n minus 1 inter-isohyet areas, right? So you have 5 fingers, you have 4 gaps between 5 fingers, right? So 1, 2, 3, 4. So same idea, right? All right, that's it. So let's go ahead and look at a problem using this. Okay, the isohyets due to a storm and catchment were drawn as shown here, and the area of the catchment bounded by the isohyets were tabulated as below. Okay, so I have isohyets stationed to 30 kilometers square, which means this area is 30 kilometers square. Then between 12 and 10 is 140 kilometer square. That is this area. This is 140 something. I'm just marking it out. Between 10 and 8 is 80. Between 8 and 6 is 180. And between 6 and 4 is 20. Okay. So now, you have to please keep in mind, this 20 is just the area that is inside the catchment. Okay. It's not the, because there's no bounding area over here. There's no intersecting line there. So you have to just take the portion that's inside the area of interest. Okay. And then the question, estimate the mean precipitation due to the storm. Fairly straightforward. Think about it. So you just take the area, add them all up. So 30 plus 140 plus 80 plus 180 plus, what is that? 180 plus 20. The total area is 450. Then I take the fraction of each of those areas with respect to the total. So if you go back to, you will see at the bottom, I have divided by A, the whole thing divided by A. What is A? What is capital A? Capital A is nothing but A1 plus A2 plus so on, AN minus 1 in this case, right? So capital A is total area. So that's why when I divide it by this, what I'm doing is A1 divided by capital A plus A2 divided by capital A plus A3 divided by capital A, and so on. That be the fraction. This fraction of total area, this column number 4, is nothing but A1 divided by capital A. So this is 30 divided by 450. 140 divided by 450, 80 divided by 450, and so on. And then you take these fractions, multiply them by the average precipitation for each of those interisohydrates. The first one, there was a station right in the middle. If you look at the figure there was a station, rainfall gauge station here, which had a rainfall of 12 centimeters. And the height was actually a circle. So that entire area is receiving 12 centimeters of rainfall. Right. So therefore, I can use the entire area, and the average itself is 12. Right. So for all the remaining ones, you take the average, 10 plus 12 divided by 2, 11, 8 plus 10 divided by 2, and so on. Right. And then you multiply them by the fractions, you get the weighted precipitation, add them all up, you get the total mean precipitation, which is 8.84 centimeters. Okay. Any questions? Any questions before we move on?
So can you explain the mean precipitation part again?
The mean precipitation part. Okay. So
Yep.
Okay. Do you want me to explain it on this slide or the next slide?
After that area slide, the 12 centimeter area.
Oh, here. Here, this column number 2.
Yes, sir.
Okay. So for, let's say, this area between 12 and 10, it says the area is 140 kilometers square. So the representative average value for between those two between those two isoheights is 11 centimeters. So let me go back to that. So this is 12. This isoheight is 12, and then this one is 10. Okay, let me maybe erase that stuff over there. Okay. So this is 12, and then this is 10, right? So the area in between 12 and 10 is this entire area, without including that little circle in the middle. Okay, this area is 140 kilometers square. Okay, and then the average for that area is 12 plus 10 divided by 2, which is 11. That area, multiply it by 11, and that gives you this 3.42, whatever it is. For the next one, between 10 and 8, this is 10 and this is 8. The area between the two is this area, right? This portion between 10 and 8. So that area is 80 kilometers square, and the average precipitation representative of that area is the mean of 10 and 8. So that's 9 centimeters. The next one is the area is 180 kilometers square, and the representative average would be 8 plus 6 divided by 2. That's 7 centimeters, and so on to the next one. The only slight deviation from whatever I have explained so far is that point D over here, where I have a station which has a rainfall of 12 centimeters, and there is an ISO height which is actually a circle, right? So within that ISO height, because it's a bounded area, and because the point in the middle also has 12 centimeters of rainfall, so therefore you can say that entire area represents 12 centimeters of average rainfall, right? Therefore, only for this 30 kilometer square area, which is that area of that circle, the average value is 12 itself, because there's a station in the middle which has also got 12 centimeters of rainfall. Okay, does that answer satisfactorily, Aditya?
Yes, it is.
Okay, thanks. Any other questions? Okay, let's move on. Now, one more way of doing this is to estimate the aerial distribution of rainfall using some kind of an empirical formula, right? So let us say I have a rainfall event of some given duration, let's say for 2 hours or 4 hours or 1 day, whatever it is, right? So then I say that the representative average depth of rainfall over that area A, you can give that by some kind of an empirical equation, P bar, which is the average, equal to P naught. I'll explain what P naught is. P naught times e to the power minus k into a power n. Okay. Now, this P naught is the highest amount of rainfall received at the storm center, right? Now, whenever there's a rainfall event that happens, right, there is a center of the storm, right? Now, the center of the storm typically receives the highest amount of rainfall. Okay, and as you move away from there, you get lesser and lesser rainfall as you move away from there, right? So this P naught typically is also representative of what is going to be the average over that area, right? So what are the factors that are going to determine what the average rainfall over a certain region is? What is the maximum rainfall received in that region? How large is that area? And then you have some kind of empirical constants that you have for each region, right? Which you can develop with data over a period of time, is to have this kind of a relationship. And what it says is that there's an exponential decay as you move away from the center of the storm, right? So whatever is received at the highest rainfall that's received due to a particular storm may not be the same rainfall that's received over the entire area, right? So for example, suppose there's a cyclone that's going to hit, I think recently there were major rainfall was received in Bombay maybe a week back or something like that, right? So then typically what will happen is there will be a particular region which receives the highest amount of rainfall, and then as you move away from there, the rainfall kind of reduces it. And then if you go 100 kilometers away, there's no rainfall at all, and so on, depending on the strength of the storm and so on. So this is one way of doing it, but again, this requires you to know multiple things about the storm. Number one, you need to know what was the highest rainfall received over that certain area. Now, it's not necessary that the highest rainfall always happens where you have a rainfall gauge. I may have a rainfall gauge here and another rainfall gauge 10 kilometers away, but the highest rainfall may happen somewhere in between. Can't do anything about that. Okay, that's one of the disadvantages of this method, is that you really don't know what the highest amount of rainfall is. But by and large, if you're close enough, you will also get a pretty significant amount of rainfall. If you're close enough to the storm center, most likely you will be getting close to the highest amount. If you can't catch it, well, there's nothing you can do about it, right? So you're limited by the data that you have, and then you can use these empirical constants that are developed for certain regions. Now, these kinds of things are mostly historical relics. These days we don't use this a whole lot, because compared to 10 years ago, 20 years ago, or 40, 50 years ago, we have so much data, right? There's rainfall gauges installed all over the place. The models have improved. More importantly, people are when they receive rainfall, people are what is that thing called, crowdsourcing. Somebody who received rainfall in some remote corner, they say, oh, I'm receiving so much rainfall in the last 5 hours. They'll post it on Twitter or whatever it is, and therefore that is a secondary source of data. That's not primary data. Primary data, you have a rainfall gauge, and and you're properly measuring it and so on. But you can also get so many other sources of information which allow us to better estimate, right? So a lot of research is actually being done on how you can improve the data quality by you have high quality data at certain locations, but at the end of the day, it's impossible to install rainfall gauges every all over the place, right? But I install as many rainfall gauges as possible for the data that I don't have, or for locations that I don't have information. Can we use, people posting their, we can give people an app and say, just note down what happens in your place and then just upload it. Now people may make mistakes. They may think that it was I received 10 centimeters of rainfall. Maybe it's only 8, maybe it's 12. They underestimated, whatever it is. But if you get enough people to contribute, if a lot of people contribute that kind of data, it's possible to extract some useful information, right? These days, that's what people do, data mining, right? What would you rather have? Would you rather have a lot of poor quality data or a limited amount of high quality data? This is the challenge that we have these days, right? So one of the findings from research that has gone into this is that high quality data is very important, no doubt about it. But even if you have a lot of poor quality data, that's better than having no data, right? So you can always do some kind of statistical technique to remove the noise from the data and then use it and so on and so forth. Okay, so nothing to do with this particular slide, but I'm just generally giving you an idea. Okay, let's move. Now, this is the aerial distribution of rainfall. This, of course, not very popularly used these days, but just giving you the historical perspective. Okay, right. The kind of the next topic that we'll touch on is this idea of the depth, area, duration curves. Okay, now a DAD curve, as it is sometimes called, uh, is a way of representing multiple pieces of information about a certain rainfall event, right? These three parameters that we look at for a rainfall event. Number one, the depth of rainfall received. That's very important. The area over which the rainfall was received. It's the second piece of information. And then the third piece of information is the duration over which the rainfall was received, right? So you have the depth, you have the area, and then you have the duration. Now, all these three pieces of information, if I can convey them, that will give me a lot of information about the kind of rain, right? So it's very useful if you want to estimate the severe floods in a region. You can use the depth, area, duration curves. I'll show you a typical example of a DAD curve, right? Of course, it requires long-term data of rainfall amounts and durations, and then you can figure out what the DAD curve for a certain region is. Okay, so now the DAD curve, on the x-axis, I have the area over which the rainfall was received, and that, as you can see, is in kind of log scale. On the y-axis, I have maximum average depth. Okay, now the terminology can be a little bit confusing, but you have to pay attention. Maximum average depth means, right? Let us say the rainfall is happening over, let's say, an area of 100 square kilometers. Okay, let us say rainfall is happening over 100 square kilometers. Over that 100 square kilometers, there is an average depth of rainfall, which is what we were talking about in the previous slides. How do you find the average depth of rainfall? You have multiple rainfall gauges. You take them, you either use Thousand polygon method or the ISO height method or whatever it is, and you find the average depth of rainfall for that particular location. Okay, now let us say this rainfall event happened for 6 hours. Over an area of 100 kilometers square, I received rainfall for 6 hours this year. Okay, and I received a certain amount of, and the average rainfall depth for that duration over that area was some number, let us say 6 centimeters of rainfall. 6 centimeters of rainfall were received over 6 hours over over 100 kilometers square. Last year, or 1 week back or 10 days back, I received another 6 hour rainfall event. Okay, over the same 100 kilometers square, and that time the amount of rainfall received was not 6 centimeters, it was 7.2 centimeters, for example. Okay. And then last year I received another 6-hour rainfall event over the same area for the same duration over 6 hours. That time I received only 3 centimeters of rainfall. Okay. So like that, suppose I have information about the different amounts of rainfall received for the same duration 6 hours over the same area 100 kilometers square for the last 50 years, right? Over the last 50 years, I would have received rainfall hundreds of times. Okay. Each time the rainfall amount will be different, the rainfall duration will be different. Okay. And then from all this, find out, I segregate the data into different rainfall events. What are all the 1 hour rainfall events? What are all the 6-hour rainfall events? What are all the 12-hour, 24 hours, 18 hours, whatever it is? I segregate it into different durations. And then from each of those durations, I find what was the average depth of rainfall received in the year 1950 for 1 hour, in 1951 for 1 hour, in 1952 for 1 hour, and so on for until 2025, let's say. So I have 75 years of data of 1 hour duration over that certain area of 100 kilometers square. And in those 75 years, there will be one maximum value, right? So I said 6, 7.2, 3 centimeters, 4 centimeters, whatever it is. And let us say the number was 12 centimeters happened once in 1982, some year. Okay. So that year is the maximum average received over that certain area, over that certain duration. And like that, I have data for different durations and for different sizes of area. Okay. Then I get this kind of a curve. Okay. Now, the first thing that I want you to think about, and let me know if you agree with this. You take any of these 4 curves, there are 4 curves there representing different durations. Why is the maximum average depth decreasing as the area of the rainfall is increasing? Do you agree with that? So for example, let us just take our duration curve. There you go. So this is 100 kilometer square. This is 1000 kilometer square. Okay, approximately I've marked those 2 points. Okay. For an area of 100 kilometers square, for a duration of 12 hours, the maximum average depth is close to 20 centimeters of rainfall. But if I look at a larger area, let's say 1000 kilometers square, for the same duration of 12 hours, my rainfall amount, maximum average depth is not 20 centimeters, it is something like 16 or 17, whatever it is, this number. Does that make sense to you? If the area of the region where rainfall is happening increases, the average rainfall received over that area decreases. Does that make sense? I'll ask it in a different way. Suppose I tell you, let us say Tirupati to Chennai, the distance is about 100 kilometers, 130 kilometers. Okay. Suppose a storm crosses between Chennai and Tirupati, somewhere between in the coast. Okay. It crosses. And then I find out with the data that Chennai received, let's say the storm crossed for 8 hours, 10 hours, 12 hours, whatever it is. Chennai received 20 centimeters of rainfall during that storm event, 12 hours. Tirupati received for the same 12 hours, Tirupati received 8 centimeters. Chennai received 20 centimeters, Tirupati received 8 centimeters. Okay. Then I draw some box around Chennai and Tirupati and say this is the area over which this storm was passing. Okay. This is my area of interest. And then I find the average depth over that area. It will be somewhere between 8 and 20. 20 is the highest which Chennai received. Tirupati received 8 centimeters. In between, I have other rainfall gauges. One place said 12, another place said 9.2, another place said 13, whatever it is. Right? And when I take the average, I'll get a certain number for that area. Now, if I draw that box smaller, okay, instead of coming 130 kilometers from Chennai, if I just say, let me draw that box smaller and draw it only 60 kilometers, half the distance between Chennai and Tirupati, will my average be higher or lower? I don't know if I made sense because the silence is scary. Okay, Ayush,
Sir, probably higher.
the average will be higher. I agree with you because I have, of course, done something there. What I did was I didn't go from Tirupati towards Chennai. I went from Chennai towards Tirupati because Chennai is where the higher rainfall was received. So it makes sense. The storm center, let us say the storm center was at Chennai, and then if I draw a smaller area between Chennai and Tirupati, halfway between Chennai and Tirupati, you will get a higher number. So the smaller the area, the larger the rainfall. The larger the area, the lesser the rainfall. That kind of makes sense, right? It is not believable if I say yesterday it rained in Chennai and Tirupati and also in Delhi. If I said Tirupati and Delhi received the same amount of rainfall or close to the same amount of rainfall, you can't believe it. It can't be the same rainfall event that produced rain in Tirupati and in Delhi because it's too far away. So far away, you won't expect rainfall to forget about Delhi. Even Hyderabad and Tirupati cannot get rainfall due to the same storm on the same day. Right? Chennai and Tirupati can get rainfall on the same day due to the same storm because they are close enough. And these sometimes the storm cyclone when it comes, the wind is at 100 kilometers per hour. So it will hit Chennai 1 hour later or 2 hours later. It will hit Tirupati. That's possible, right? But it can't travel 600 kilometers, 1,000 kilometers, 3,000 kilometers. By that time, it will lose its moisture, right? So the larger the area, the lesser the rainfall. So that makes sense. So I'm assuming that everybody understands why all of these curves are going down as area increases. How about as duration increases, all the depths are increasing with time. Does that make sense? The longer the rainfall, the more the rainfall received. The longer the duration of rainfall, the larger the amount of rainfall received. That makes sense, right? I'm sure that makes sense. These two aspects you have to look at. You take any curve, you can see that it is decreasing with increasing area. You take any given area and you draw a vertical line. So let me draw a vertical line here. As the duration of the rainfall increases, the amount of rainfall received also increases. That also makes sense because these are the maximum average depths, right? It's possible that one particular year in 1 hour I get a lot of rainfall, in 12 hours I get very little rainfall, but over a long period of time, it's more likely that I'll get lot of rain in 12 hours than in 1 hour, right? So it's probabilistically speaking, it makes sense to think of it that way. I mean, unless there is some unheard of once in a million years rainfall event, well, then nothing we can do about it. This is all based on from 50, 60, 70 years of data. If something that no human being has ever seen or ever recorded happens, then we can't do anything about it, right? So whatever planning we do is for once in 100-year event or once in 200-year event or something like that. We can't do anything about once in 1,000-year event or once in a million-year event because it's too far back. Nobody knows what happened 1,000 years back, 10,000 years back, and so on. Okay, let's move on. Now, as soon as I say that I know how much is the maximum rainfall that can happen over a certain region for a certain duration and so on, the next question that becomes interesting to me as a civil engineer who has to plan the size of my infrastructure and so on is the frequency of occurrence. How often will such an event happen, right? Because depending on how often it happens, I'll have to plan for it. I can't just say, oh, we'll see what if it happens, it happens. What can I do? No, you have to know how often it happens so that you can take some steps to address those problems, whatever problems may arise because of that, right? So we need to know how often will this kind of extreme event happen so that you can plan for the floods, right? Otherwise, it becomes impossible to plan. So the way it's done is by assuming that rainfall is some kind of random process, right? We assume that rainfall is a random process. So whenever there's a random process, then there's a way of figuring out the probability of occurrence, right? So I'm going to demonstrate one way of doing it. This is fairly straightforward method for doing it, and and there are many ways of doing it. This is we are going to just go through one typical way of doing it. You can read up about more sophisticated ways of doing it, or more elaborate ways of doing it. Things are available in textbooks and so on. Right. So what you do is, the first thing you do is you have a data set of extreme events. So you collect the data for the last 50 years, 80 years, 100 years, whatever you have, of all the extreme events that have happened at a particular location for a sufficiently long time, right? So most of India, we have rainfall records from, let's say, late 19th century, early 20th century, which means around 1880s is when the British started to, start recording data and very locations, right? And then by 1910, 1920, 1930, we have more and more data becoming available. Of course, most of it is, not very easily accessible to us, but government departments have these data sets and so on. But after 1950, 1960, data is more reliably available for almost the whole of the country at different resolutions, right? So then I pick out all the extreme events that have happened over this duration, right? I'm not interested in merely knowing the average event that happened. I want to know the extreme event that happened. Okay, I find out what is the probability of occurrence of this extreme event. I do what is called the frequency analysis of this data series, right? Because I have data for the last 50 years or 80 years or whatever it is. And using that data, I do a simple kind of frequency analysis. And that frequency analysis allows me to estimate the probability of occurrence, right? If the probability of occurrence of a certain event is known, if the probability P is known, then I can find out the return period. Now, the return period is just a statistical way of saying how often will this kind of a extreme event occur again, or how much time does it take for an extreme event to return. It came this year, it'll return after 5 years, 10 years, 20 years, whatever it is, right? So we can refer to it as the return period or the recurrence interval. All these terms mean more or less the same thing. So I want to know the return period of a extreme event, which is 1 by P, which is the probability of occurrence of that extreme event. Okay. Formula that we use to do this is called the Weibull formula. Okay. Very simple, pretty straightforward. Let me just quickly go through it. So what you do is arrange your data in descending order. Let's say I have data for the last 50 years of extreme rainfall received in Tirupati uh, over one day for the last 50 years. Suppose I have that. Then I just arrange it in descending order. In the year 1970, I received 25 centimeters of rainfall in one day. In the year 1989, I received 23 centimeters in one day, and so on. I just arrange it in the year where I got the highest rainfall. I just realized that 1970 was not 50 years back, it was 55 years back. Oh my God, you're getting old. I'm getting old. So you arrange all that data in descending order, and then using the information, using these n number of data points, you figure out what the probability of occurrence is. So we'll just explain what it is. So you assign a rank or an order number for every entry, right? It sounds very abstract now. When I show you an example, it'll be like, oh, this is not all that difficult. It's fairly straightforward. You assign a rank order. So the one which is the largest number will get rank 1. The one which is the next largest will get rank 2, 3, 4, 5, all the way up to n. The one which has the least amount of rainfall received in that one day over the last 50 years or 100 years, whatever it is, that will get capital N, which is 100, let's say, if it's 100 years of data. Right? Okay. I think something happened and I froze for a couple of seconds. Back now. Can you hear me? Please confirm that you can hear me. Okay, thanks for the thumbs up. Okay, so the probability of exceedance for any given event is given by m by n plus 1. M in the numerator, which is the rank or the order number for a given entry, and capital N is the total number of events. So I divide it by n plus 1. Now you might wonder, why should I divide it by n plus 1? Why can't I divide it by n? If you do that, then you will get 100% probability for the last point. Okay, and then nobody can say that you will not get less than the highest. Okay, please mute yourself. Somebody is on a. Okay, thank you. So the probability of exceedance is given by m by n plus 1, and the return period is simply 1 by p, as we already discussed. So it will be n divided by m. Okay, so let's do one simple, and then that will make it very easy to understand. Okay, the record of annual rainfall station A covering a period of 22 years is given below. Estimate the annual rainfall with return periods of 10 years and 50 years. What would the probability of an annual rainfall of magnitude equal to or exceeding 100 centimeters? What would be the probability of an annual rainfall of magnitude equal to or exceeding 100 centimeters occurring at station A? And what is the 75% dependable annual rainfall at station A? So 3 different ways of asking more or less the same information. This is the information that's given to us. So you have data for about 22 years, and I have rainfall received in each of those years for that particular location. Okay, so the first thing I do, arrange the whole thing in this, right? So I arrange it in descending order. So highest is 160 centimeters, then 143, 130, 125, and so on, all the way down to 60 centimeters, right? So that's the 22nd. So after I arrange it in descending order, I give these ranks small m, right? So the highest rainfall is 160. I give it a rank 1, 2, 3, 4, 5, and so on, all the way down to 22. So that's the last row. Then the probability of occurrence for each of these is m divided by n plus 1. So it is 1 divided by 23, because 22 is the number of data points that we have. So I have 0.043 or 4.3% occurrence, and then 8.7, 13, and so on, all the way down to the last point is 95.7. So if I had done m by n, I would have got 100% or one probability of 1, and then that's not it's not theoretically correct, because there's a chance that I may get even less than 60 centimeters of rainfall. I may get 59 next year. So you can't say 100%. We don't have that kind of certainty. So that's why we divide by n plus 1. Okay. And then once I have the probability, I calculate the return period simply by inverting it. T equal to 1 by p. So that gives me in years. So once in 23 years, I'll get once. Now remember, this probability is an exceedance probability, which means the probability of 4.3% or 0.043 is the probability of annual rainfall of greater than or equal to 160 centimeters happening at that location, right? Similarly, at that same location, what is the probability of occurrence of rainfall exceeding 120 centimeters, greater than or equal to 120 centimeters? It will be 21.7%. Here, 120 centimeters, 21.7%. What is the probability of occurrence of a rainfall of 90 centimeters? You come over here, it's 52.2%, right? 50% or close to 50% likelihood, right? So I ask you a question: what is the probability of occurrence of 70 centimeters? Okay, it's not mentioned here. I only have 60 and I have 75, 70 between. What would you do? What's the simplest thing you can do? Just interpolate between the two. 60 and 75. 70 is kind of 2/3 of the way. So it'll be between 95.7 and 91.3, somewhere in between. How do you find that out? You linearly in the two. Whenever you are asked for a number, you can always interpolate between the two. So in this case, for example, this rainfall of 89 centimeters has been received 2 times in those 22 years. An annual rainfall of 89 centimeters has happened 2 times. So when you have the same rainfall event happen twice, the probability of occurrence, you will do it for the lower rank or the higher rank, right? Not for both 13 and 14, because then it won't make sense. So for the same event, you can't have two probabilities. You can only have one probability. So you have to take it for the one which has the higher rank, which means the second or the third year where the same event, same random event happens. Okay, and so therefore the return period will be calculated only for the higher probability, not for the lower probability, right? So that's just an example of this. But the question was, I think the question asked was estimate the annual rainfall with return period of 10 years. Okay, so come over here and then look at the data. I have a return period in this column number 1, 2, 3, 4, which gives me 23 years, once in 23 years, once in 11.5 years, once in 7.6 years, and so on. So the question was return period of 10 years, again, which is not there in the data, right? I mean, whatever my numbers are, I don't have a period of 10 years. So what can I do? I can simply take the linearly interpolate between these two and find the rainfall between 130 and 143 centimeters. It will be close to 143 centimeters. So for t equal to 10 years, the rainfall is, after interpolation, you get the rainfall as 137.9 centimeters. Okay. Then it asked for a more dangerous thing, which is to say, what is the return period of 50 years? I only have 22 years of data. How can it for 50 years? Well, if this is what I have to extrapolate, right? So if I linearly extrapolate beyond 23 years, then it means that I can, I mean, of course, using the same idea of just like you interpolate, you can also extrapolate. So you just extend the slope towards a return period of 50 years and then find out what is the rainfall for which that happens, right? So that answers the second part of the question. And then the third part of the question was, what was the question? Okay, for rainfall of 100 centimeters, what is the probability? Is that how it was asked? Was it framed? What would the probability of an annual rainfall of magnitude equal to or exceed 100 centimeters occurring at station A? Yeah. So what is the probability that a rainfall event of 100 centimeters or more will happen? So again, I go back to the table. I notice that I have 96 centimeters and I have 102. I don't have 100. So the probability must be between these two, 0.435 and 0.391. So again, what do? The only I can do is to linearly interpolate between the two. So it's somewhere in between 0.1% or so and so. And then the last part of the question was, what is the 75% dependable rainfall? Now, how do I figure that out? What is the 75% dependable rainfall at this location? What does that mean, first of all? What does it mean to say, what is the 75% dependable rainfall magnitude? What is the 75% dependable annual rainfall magnitude? What will you say? Anybody? %75 dependable means, what is the rainfall for a probability of 75%? Which means 75% of the time I will receive at least this much rainfall. I can depend on that. Based on this data, I can depend on the fact that I will receive this much rainfall at least with a probability of 75%. So it will be somewhere between the 78.3 and 73.9. It will be between 80 and 83 centimeters. So again, it's an interpolation. You get 82, 82.3, somewhere in between. So that's my the 75% dependable rainfall. So it's just the procedure is fairly simple. You take data, arrange it in descending order, and then give it ranks or order number from 1 to n, whatever that is. And then to find the probability, you just have to do m by n plus 1, right? Not very hard. And then the return period, simply take the probability and take the inverse of it, 1 by p. That gives you the return period in years. Okay. So this is kind of the very last. I'll leave you with this. maybe we'll discuss this in the next class before we move on. Okay, so these are, I'm going to share these slides with all of you. Take a look at these, what is called the intensity duration frequency curve, IDF curves. Okay, take a look at them, and then when we meet again on Wednesday, I'm going to just spend some time on this, and then we'll move on to the next topic. Okay, take a look at them, try to understand what curves are trying to tell us, and then we'll take it from there. Okay, thank you very much, take care, and see you all on Wednesday.